up until now, we've been working with polynomials that have had real zeros. That's a real number, something that's either positive or negative or zero, that we can plug in and it makes the polynomial zero. But there's another set of numbers called the complex numbers. It includes the reals. So all of the real zeros that we've had have also been complex numbers, so they've been complex zeros. But the complex numbers also include some numbers that are not real. And those are going to be numbers that aren't strictly positive or negative, but are also non-zero. Okay. Now, in theory, this is something that you've seen in either an intermediate algebra or an advanced or algebra 2 class. But as placements into this class have changed, it's possible that some of you haven't seen this topic before, or it's possible that some of you saw it a long time ago and haven't really looked at it. I imagine this is one of those topics where people's familiarity and comfort level with this topic are going to be vastly different. So what I'm going to do in this video is I'm going to just do a quick review of the complex numbers. I'm going to present them as if you've never seen them before, but I'm going to go a lot faster than I would if I thought everybody was actually seeing them for the first time. So I'm pointing out that section R6, the first chapter is called R for review, and the 6th section of that chapter is entirely devoted to complex numbers. Some of you may want to look through that to spend a little bit more time familiarizing or refamiliarizing yourself with this topic. And it is one where I expect that the ability levels and the comfort levels in the class are going to be very, very different. So if you feel like you need additional time on this topic, don't feel like there's anything wrong with you. That's to be expected because people are coming in with somewhat varied backgrounds. Just consult this and let me know. Something I'd love to spend more time on with you on in office hours or by appointment. So if you need more time getting comfortable with the complex numbers after watching this video, consult this, consult me, make sure you get there. Okay, so the first thing is I need to define the number I. I is by definition the principal square root of -1. Now right there, that tells us it is not a real number because in the real numbers you can't take square roots of negatives. Okay. Now a consequence of this is that I squared will be -1. So it's almost like I is a number that's half positive and half negative. And when you have two of them, those two half negatives come together to give you a whole negative. Okay. Now sometimes students see this and they say, why do we do this? Is it just mathematicians trying to torture us? The answer is no. Why should we assume that everything has to be positive or negative, with the obvious exception of 0? Why do we have only two options? Why can't we have a richer sense of numbers? And the answer is we can. A lot of times, in a lot of applications, it makes sense that things are either positive or negative. Very often we do have one extreme or the other. But there are actually applications in physics where this is corresponding to things that exist in the real world. And also, sometimes, even if I'm trying to solve a problem with real solutions, it's easier if I allow myself to work in the complex numbers, because some things work out more nicely in the complex numbers than in the real numbers. Okay. So, we're going to allow ourselves to work with this. We call I the imaginary unit. It's an imaginary number. That's why we call it I. Okay. And the complex numbers are everything that we can build using the real numbers and the imaginary numbers together. So a complex number will always be A plus BI, where A and B are real numbers. Okay. We say A is the real part and B, which is a real number, it's the coefficient in front of I, B is the imaginary part. Imaginary part. Okay, and so I'm allowed to combine it with real numbers. Either I can multiply it by a real number or I can add a real number to it. When I do that, I get this bigger set of numbers called the complex numbers. Okay. And in the complex numbers, we are allowed to take square roots of negatives. Now, standard form is never going to involve a negative under the radical. Standard form is always going to be rewriting that in terms of this number I. So if I had the square root of -4, the fact that it's a negative tells me it's going to be an imaginary number. So the negative under the radical just becomes an I, and then I've got root 4. This would be 2I. Okay. So I will always simplify a negative under the radical in order to get that. The reason for that is I'm really used to a property of real numbers in a property of roots in the real numbers that's not true in the complex numbers. Okay. Now if I look at the square root of -4 and I want to square that, well, if I square a square root, I should get the number under the radical. So this is going to be -4. Okay. If I were to try to write that as the square root of -4 times the square root of -4, I'd be very tempted to say it's the square root of +16, because I'm used to, in the real numbers, being able to do the multiplication under the radical and just put it under one big root. That's something that's only true if both numbers are positive. Okay. So that's something that's true in the real numbers that is not true in the complex numbers. So I can't just consolidate this into one root. If I rewrote this as 2I times 2I, I could say that's 4I squared. I squared is -1, so that's 4 times -1, and that gives me what I should be getting, that if I square the square root of -4, I will get -4. Okay. But to avoid making this mistake, because it's so easy to do, we simply won't write things this way. We'll always rewrite them in terms of I. Okay. Now, where the complex numbers are going to show up for us are almost always when we're finding zeros of a quadratic using the quadratic formula. Okay. So let's just suppose I had P of x is equal to 2x squared minus 5x plus 10. Okay. I could try to factor it. I will fail. It does not factor. Okay. At least not over the integers, not even over the reals. Okay. So I would use the quadratic formula if I wanted to try to find the zeros and then be able to factor it. So I'm going to do two things. I'm going to write the zeros, and then I'm going to write P of x in factored form. Okay, so to find the zeros, I would say A is 2, B is -5, C is 10. All right, so x would equal, the opposite of b would be 5, plus or minus the square root. Oh, I'm sorry. I like to write out the formula first and then plug in. The opposite of b, plus or minus root b squared minus 4ac, all over 2a. So the opposite of b would be the opposite of -5 is 5, plus or minus the square root of 25 minus 4 times 2 times 10, all over 2 times a is going to be 4. So that's 5 plus or minus the square root of 25 minus 8 times 10. That's 25 minus 80. That's going to be -55. Okay, all over 4. All right, now I need to rewrite that. That's going to be 5 plus or minus I times the square root of 55 all over 4. So if there's a negative under the radical like this, I know that this root is going to be an imaginary number, so the entire zero is going to be a complex number. Now, there aren't any perfect squares that go into 55, so that's simplified as far as it can go. Usually when I'm writing a complex number, I would write the coefficient of I in front of the I. Often, though, when I've got I times a square root, I will write that square root after the I. That's just because if I were to write root 55 times I, it's really easy to accidentally extend that square root sign so that it looks like the I is under the square root. And I want it to be very obvious that it's not. Okay. Now, standard form for a complex number is real part plus I times the imaginary part. So I'm always going to distribute that division. So this would become 5/4 plus or minus I times root 55 over 4. That would be standard form here, and those would be my zeros. 5/4 plus or minus I root 55 over 4. Okay. That's actually something, anytime you use the quadratic formula, even if this was real, you can always distribute the division, and then you can reduce each fraction individually. So if you find yourself ever tempted to cancel across the addition or subtraction, this is always an option you have. You should, for complex numbers, always distribute that division, just because that's the definition of standard form. Real part, just a purely real number, plus or minus I times the imaginary part. Okay, so that's what we're going to have most of the time. That's where we're going to see these complex numbers showing up as zeros of a quadratic that we get using the quadratic formula. Okay, you'll notice these guys have an awful lot in common. It's just the plus or minus sign. Okay. So given a complex number, a plus bi, its conjugate is a minus bi. Okay. Same real part, exactly the opposite imaginary part. We call that the conjugate. So when you've got this plus or minus something here, this is a pair of complex conjugates. And we'll see in the next section that if I'm working with a polynomial with real roots, with real coefficients in the original polynomial, when I find the zeros, if they're complex, they will come in pairs like this. Okay, that's kind of nice. All right, so I said I wanted to do two things. I wanted to find my zeros, which I did, and then I wanted to write p of x in factored form. So just like the last example where we used the quadratic formula, except there we got real numbers, they were just kind of messy, I can say I know if I have a zero, I have a corresponding factor. So we're going to have x minus, now be careful, 5/4 plus I root 55 over 4 is one factor, and x minus, I'm putting the whole zero because it has two parts to it, I'm putting it in parentheses, 5/4 minus I root 55 over 4. Those are two of my factors. If I look right now, there's a little bit more I need to do. I can see right now my lead term would be x squared, but I want my lead term to be 2x squared. So there's an additional constant factor of 2. And then I'm just going to simplify by distributing the negative in each of these. So I would have x minus 5/4 minus I root 55 over 4 times x minus 5/4 plus I root 55 over 4 times 2. So that would be this fully factored over the complex numbers. If you are just told to find the zeros or to factor, in this textbook you are working over the complex numbers. I will sometimes be more specific. In the next example, I'm going to tell you to find all the real zeros and find all of the zeros. So when we're finding just the real zeros, we would ignore anything that was complex but not real. I should point out, real numbers are part of the complex numbers. Real numbers would just have their imaginary part, this b being 0. So the complex numbers include the real numbers. It's just a bigger set of numbers with slightly different rules.